As outlined by the theme information given by the Rascal competition, the primary objective of the mission is to provide acceleration due to gravity the same as Mars, or 3.711 meters per second squared, for a crew of 48 people for the majority of an approximately 1,100-day round trip. The design requirements of the spacecraft are it must be able to support a minimum 15-year lifespan, to which during that time a minimum of 3 round trips must be performed.
The total mass of the habitational modules will be at minimum 49 tons. This requires that at least 22 tons of habitational weight experiencing artificial gravity will be there, and 27 tons for logistical weight will be included. Additionally, the spacecraft must be able to transport separately a fully burdened Mars lander rover, which is estimated to be 50 tons. This must be done departing and returning along the same path lines as a crewed mission. Morty will begin its construction in January of 2028 through a series of 4 launches to low Earth orbit. After assembly, Morty will maneuver into cislunar space for Martian departure. En route to Mars, the extension of the transfer bridges will begin artificial gravity rotation. Upon entering Martian orbit, the transfer bridges will retract. The launch vehicle is responsible for sending a payload into space from the surface of the Earth. Due to mission requirements, the baseline habitats and the Bigelow B-330 will be launched from either a NASA-built Block 1A or Block 2B SLS. For this mission, the Block 1A was chosen for its outstanding payload capabilities. Shown here is a rough illustration of what the Morty will look like after final assembly. It should be noted, however, that this depiction is not made to scale. After construction, it is estimated that the Morty will weigh roughly 360,000 kilograms and enclose a habitational volume of 490 cubic meters. After the 4 SLS construction launches, time invested, research and development, and cost of materials, it was calculated that the Morty will cost $52 billion to assemble. In the center console will lie the Bigelow-made B-330 habitat. Attached to that will be 2 transfer bridges, each with 1 cislunar habitat at the end. It is here that the Martian gravity will be simulated. To propel the Morty, a liquid fuel propulsion system and roll-out solar arrays will be added to the back. The total system will experience an RPM of 4, which will ensure the ideal gravitational simulation. The gravity will be simulated by thrusters on each cislunar habitat applying small microthrusts to achieve the Martian gravity. Shown on the left is the Bigelow-made B-330 habitat. It has a mass of 10,400 kilograms, a width of 7 meters, a length of 17 meters, including the propulsion system, a volume of 2,380 cubic meters, a max cargo capacity of 63,500 kilograms, and a power consumption of 28 kilowatts. On the right, a cislunar habitat is shown. This has a mass of 5,000 kilograms, a width of 4.5 meters, a length of 6 meters, a volume of 64 cubic meters, and a single one will be able to house a crew of 4, while 2 will be able to house a crew of 6. The power consumption for each habitat was calculated to be 7.3 kilowatts. There will be 2 transfer bridges on the Morty, each with a length of 21.13 meters. The architecture of the transfer bridge will consist of 7 aluminum rings made out of aluminum 2024. Each ring will have an inner diameter of 1 meter and an outer diameter of 1.254 meters. The 7 rings will be spaced evenly throughout each transfer bridge, with 1 being on the Bigelow, 1 being on the cislunar habitat, and 5 running throughout the transfer bridge. These rings are designed to house and stabilize the rigidity of the transfer bridge. Along the length of the transfer bridge will be a collapsible beam of undetermined material, which is designed to allow the cislunar habitats to collapse and expand in order to simulate various artificial gravities. The aluminum of one transfer bridge will be 16,600 kilograms and have a space blanket of 14,300 kilograms.
For the propulsion subsystem, Rascal requires that the team use both electric propulsion and chemical propulsion technologies. It was determined that the chemical propulsion technology would be the Morty spacecraft will use SpaceX's Raptor engines for major orbit keeping and orbital insertion and escape. These engines were chosen because of their thrust, which is about 3 million newtons, and for its propellant types, which is methane and oxygen, which allows Morty to refuel on Mars. The orientation thrusters will use the same propellant type to reduce complexity and weight by eliminating extra fuel tank. For the electric propulsion requirement, the Morty spacecraft will use Hall effect thrusters, which give a long lifespan, high ISP, large thrust, and will be used to maintain rotational stability and minor gradual orbit keeping.
For life support systems, our mass estimates were 15,500 kilograms of water, 11,000 kilograms of food, and 3,700 kilograms of oxygen. Currently, the ISS can recycle 42% of oxygen and 90% of water. However, for our Mars mission, we need at least 75% oxygen recovery and 98% water recovery. One solution to this problem is creating the solar electric propulsion tug unit that can carry multiple resupply units to and from the orbit of Mars. We investigated two more systems for oxygen and water recovery. The first is the vapor phase catalytic ammonia removal system, which has a high efficiency but is not very reliable. The second is a temperature swing absorption compressor, which has a 95% oxygen recovery rate. However, it has not been implemented in the ISS yet.
The power subsystem is split into two main components, the battery assembly and the solar array. For the battery assembly, we have chosen to use lithium-ion because it is half the size of the nickel-hydrogen generally used on spacecrafts, but has double the power capacity. As for the solar array, we have decided to use the ROSA, or the rollout solar array. The ROSA is about half the size of a traditional fold-out solar array, and can generate about 114 kilowatts each for a total of 228 for the entire system. These solar arrays will trickle charge into the battery assemblies. Due to their tendency to overheat, we have decided to use a set of 3 and 3 battery assemblies for the lithium-ion. This way, while 3 are always charging, the other 3 can be discharging. This allows for a constant flow of energy throughout the spacecraft, without creating a fire hazard for the crew. The thermal subsystem is split into active and passive controls. The active control system is made of heat collection, heat transportation, and heat rejection. Heat collection involves electric heaters placed on equipment in order to get them to the operating temperature. From there, any excess heat is transported throughout the fluid loop system. The fluid loop system absorbs the heat into the liquid and transports it through things called heat pipes. These heat pipes run throughout the entire spacecraft and allow for easy heat transportation. From there, the heat can be rejected through radiator panels. These radiator panels are about a quarter of the size of the ROSA and located directly beneath them for ease of heat transportation. Each set of arrays has the ability to reject up to 7 kilowatts of excess power, resulting in a total heat rejection capability of about 35 kilowatts. The passive control system is comprised of the non-dynamic components of the thermal control system. This includes things like insulations and coatings that protect from the extreme temperatures of space.
Morty will be making use of two Terma HE5AS star trackers. Star trackers work by taking pictures of a star field and comparing it to a star field stored on the processor unit. The differences are sent to the onboard computer and course corrections are made. The reason why the Terma star trackers were picked over all the others were its wide aperture field, low cost, and the fact that its camera and processor are separate. Its wide aperture field allows for more precise measurements to be made, as more stars can be compared to each other. The separate camera allows for easier placement on Morty. The course corrections calculated by the onboard computer will be executed by several attitude control thrusters placed strategically along Morty so as not to affect its artificial gravity rotation. These adjustments will be vital in ensuring that Morty reaches the exact attitude needed to enter the 5-Sol Martian orbit when it reaches Mars.
For the command and data handling subsystem, I looked at 3 different computer processors, the Mongoose V, RAD 750, and the RAD 6000. I compared the price, power, heritage, radiation hardenability, year, versatility, and speed. These generated scores using an algorithm I made in a trade study, and the best result came from the RAD 750. So we are deciding on using the RAD 750 for this project. It's about 200,000 per unit, and due to redundancy, we'll probably have 2, which would come out to be 400,000. It uses 5 volts of power and has approximately 200 megahertz speed. And this will be able to take input from several different sensors. In the future, we'll be looking at new processors being formed and whether or not we can implement those by launch date.
All ground control operations for this mission will be run out of the Johnson B Space Center. Founded in 1961, it has been in charge of every single manned NASA mission. It is this outstanding track record that makes us confident in their abilities to handle this mission. The Space Center will be in regular contact with Morty, ensuring that all life support signs and all attitude headings are correct. Any inconsistencies will be dealt with by the crew at the Space Center, and fixes will be relayed back to Morty's onboard computer. Furthermore, the Johnson Space Center is the ideal place to handle any and all emergencies that may occur during the trip to Mars. As this mission involves a human crew traveling in interplanetary space to Mars, it is vital that these emergencies are dealt with effectively and efficiently. The Johnson Space Center is by far the best place for these responses to be calculated and sent back out to Morty in order to ensure the safety of the human crew.
This mission will incorporate the collection of data through voice, video, and crew health measurements. Key requirements for this communication system include the ability to communicate with various institutions on the Deep Space Network, prioritization of data streams, reconfiguration of the communication system in response to changing requirements, and robustness during temporary outages throughout the course of the mission. Morty will be communicating with the Deep Space Network primarily through the X-band, which transmits data at 8 GHz. However, depending on the progress of research, the 32 GHz Ka band may also be used. The onboard communication system will consist of 1 parabolic dish high-gain antenna and 4 low-gain antennas. The high-gain antenna will be used for communicating with Earth throughout the building process and up until Morty is on its home and transfer to Mars. Once that transfer has been initiated and the rotation has begun, Morty will switch to the low-gain antennas with 1 transmitting data and another receiving data. The extra antennas will serve for redundancies.
In conclusion, the Morty will weigh approximately 360,000 kilograms without a payload, have a habitational volume of 490 meters cubed, draw 558 kilowatts of power, and cost $2.19 billion in material and $52 billion total. It will be spun at a rate of 4 RPM to achieve Martian gravity of 3.711 meters per second squared, with the habitats being 21.13 meters away from the center axis of rotation. The retractable transfer bridges will expand soon after leaving cislunar space in order to provide the necessary radius, and solar power provided by ROSA will enable the life support systems to keep the human cargo alive and healthy for the duration of the long trek. A combination of star trackers and a communication array will ensure Morty will reach Mars on course for an extended Sol orbit.